Lighthouse Scientific Education presents a lecture in the Atomic Structure series. Topic is order in matter. Order in matter deals with the underlying principles relating energy and matter and the numerical relationships that come when matter interacts with matter. We will begin with a description of the chemical equation. That's writing out chemical reactions. These reactions follow the law of conservation of mass and energy. We will see that the compounds come in definite proportions and that there is a law of multiple proportions. And finally, we will combine these laws and concepts into Dalton's atomic theory. First, the chemical equations. Chemical equations represent the sentences in the language of chemistry. Much of the study of chemistry has at its heart a chemical equation. An example, 2 hydrogen molecules combine with 1 oxygen molecule to form 2 water molecules. A chemical equation is the means of communicating a chemical change. It uses symbols and formulas to represent the elements and compounds involved in the chemical reaction. The 2 H2s plus 1 O2 becoming 2 H2Os is a formula. 2 important terms in chemical reactions are reactants and products. Reactants are the species present before the reaction. In chemistry, the term species just means the atoms or compounds involved in the chemical process. Products are the species present after the reaction. Products make sense as a term for what comes out of a reaction. The arrow means yields or reacts to produce. It is sometimes replaced with a double-headed arrow or 2 opposing arrows. These 2 later arrow types communicate that the reaction goes in both directions. More on that later in the course. On to the law of conservation of mass and energy. First, to the conservation of mass. In an isolated system, the total amount of matter remains constant. Isolated is a situation where nothing can enter or leave. Another way of stating the law of conservation of mass is matter cannot be created or destroyed. It can change forms. We saw the hydrogens and oxygens change form and become water. No matter was created or destroyed. The importance of this law is that all matter must be accounted for in a chemical reaction. As such, the mass of the reactants must equal the mass of the products. That actually makes the process easier. Similarly, the conservation of energy says that in an isolated system, the total amount of energy remains constant. And that means energy cannot be created or destroyed. It can change forms. Lift a ball over your head. The energy required to raise the ball is now in the ball. Let go of the ball and see the energy at work. There is one caveat to these 2 laws, and it doesn't really come into play at this level of chemistry. And that is E equals mc squared. Energy equals mass times the speed of light, c, squared. Matter can be changed into energy and vice versa. We owe Einstein a nod for this one. But as stated, at this level of chemistry, the laws of conservation will almost always hold. So, bottom line, conservation means that the total amount of energy and mass in the universe is set. It is a constant. A very important milestone in the understanding of chemistry was the development of the law of definite proportions. The law of definite proportions is known as Proust's law. It states that every definite compound always contains the same elements in the same proportions by weight. Returning to our favorite compound, water, it always has 2 hydrogen atoms and 1 oxygen atom, H2O. And getting just a little bit ahead of ourselves, when viewed by weight, water is composed of 8/9 oxygen and 1/9 hydrogen. and that's because oxygen is a lot heavier. The study of chemistry would be much harder than it is if every time we dealt with water, we had to figure out its oxygen to hydrogen proportions. Nature, it seems, keeps a tidy house. That is not to say that it doesn't get more complicated. The law of multiple proportions. When two elements combine with each other to form more than one kind of compound, the weights of one of the elements, which, when combined with the fixed weight of the other, is in a ratio of small whole numbers. Yes, it is a mouthful. Not to worry though, a simple demonstration will help clarify the point. Consider the following two reactions. 2 hydrogen molecules plus 1 oxygen molecule forms 2 waters. And 1 hydrogen molecule plus 1 oxygen molecule forms 1 hydrogen peroxide molecule, H2O2. Both reactions involve hydrogen and oxygen. The two elements can combine with each other to form more than one kind of compound. Okay, now for that fixed weight part. We say that in both reactions, we start with 16 grams of oxygen. 16 grams of oxygen in the first reaction, and 16 grams of oxygen in the second reaction. That is our fixed weight of the other. Now to the first element, hydrogen. In the first reaction, we need 2 grams of hydrogen to go with that 16 grams of oxygen. Why this is so is a subject covered later in the course. Just accept it for now. For the second reaction, we will only need half as much hydrogen, 1 gram. If we look at the ratios of the weights of hydrogen in these two reactions, under the condition of holding the weight of oxygen fixed, we find it to be 2-to-1 ratio, a ratio of small whole numbers. What this law leads to is that elements or compounds have a set weight and combine in set proportions. The development of the laws and concepts that we covered here led to an important early theory of the atom. In 1803, John Dalton summarized these basic laws into the first modern theory of the atom. That's only 200 years ago. Dalton's theory would become the bedrock of modern chemistry, but modifications would follow. He postulated that all matter is composed of atoms. Not a new concept, goes back to the Greeks, but an essential component of this theory. Next, atoms cannot be made or destroyed. Law of conservation of mass. All atoms of the same element are identical. All carbon atoms are alike. Different elements have different types of atoms. The element oxygen and the element hydrogen have different types of atoms. Chemical reactions occur when atoms are rearranged. Law of definite proportions, law of multiple proportions. And finally, compounds are formed from the atoms of the constituent elements. Law of definite proportions. Water is composed of the elements hydrogen and oxygen. It is made up of 2 hydrogen atoms and 1 oxygen atom. Note that this is a summary of Dalton's theory, and that some textbooks will present the theory with minor variations. Also note that there have been some modifications to the understanding of the atom over the last 200 years. So while Dalton's work is groundbreaking, it is a bit dated. And that completes our lecture. To recap what we've covered, chemical equations represent the sentences in the language of chemistry. Reactants are the species before the reaction. Products are the species after the reaction. Conservation of mass. Matter cannot be created or destroyed. It can change forms. Conservation of energy. Energy cannot be created or destroyed. It too can change forms. The law of definite proportions. Every definite compound always contains the same elements in the same proportion by weight. Water is 16:2, oxygen to hydrogen. The law of multiple proportions. The weights of one of the elements, which, when combined with a fixed weight of the other, is in a ratio of small whole numbers. And finally, In 1803, John Dalton summarized these basic laws into the first modern theory of the atom. This lecture covered many fundamental principles of nature. Be sure to review the material so that you can use it as a foundation to build upon.